equations for the MOSFETs, yani what they are, because this will allow us to somehow do the analysis that we are interested in terms of delay, in terms of sizing, in terms of power analysis and noise analysis, etc. And after we study this IV characteristics, okay, we are going then to look at the fabrication, how it is done, and the layout, and jump back up a little bit to the logic level. So we're going to go down into the devices and then go back up into the logic level. Hello. In the coming week, we will have some problem solving about the IV characteristics, which will be included in the short quiz. I will do a problem solving session, and I will send you an email where some of you may start to attend the CAD session with Miss Basma, which is like similar to a mini lab, which you will get some grades for attending it, and the results of the simulation that you do in this CAD session will be considered in your as part of your grading, because there will be some homework questions about it, meaning you will report what you simulated during the CAD session, during the mini simulation session with Miss Basma, and she will be guiding you through that effort. Okay, so now so this is why the reason why I'm shifting a little bit to the current characteristics. So we are all familiar with basic linear devices, and the simplest devices in R والcapacitor والinductor R, L, and C, and for this the equations are physical and they are very well defined. However, we have nonlinear devices like the transistor or the diode, and for these nonlinear devices we want to abstract them somehow, so that either we can build models so that we do first order hand analysis, يعني مثل linear model أو quadratic model اللي نحن كنا ندرسه in 311 or 310, and we also can have some sophisticated models for the computer analysis, which are typically used by the simulator. يعني بس هلا عم بعطيكم هيك basic background what options we have to build these models. Okay, so we are not going to study diodes in this class at all, but I'm just trying to tell you that the diode is really the simplest two-terminal device. The way we build it, since it is a p-n junction, I will have an n-type substrate, and I will plant P material, and I will tap from A to B. What matters for me, in your mind, you know that the metal here is connected to the N-type, and the metal here is connected to the P-type. So really it can be envisioned in this form. A metal is connected to the N, and a metal is connected to P, and this is the symbol, okay? And from this symbol, we derived in the previous classes the model, but we need to know that a basic model will have some parasitics in addition to the simple functionality. طبعا we're not going to use this equation, but I'm just trying to tell you that when we studied this, we said that the I diode is equal IS e to the VT VD over NVT, right? So these are equations, and those equations are really a model that I obtained for the device behavior, just like I'm saying Y is equal to the E to the AX over C. Okay, so X is my input and Y is my output, and we defined that it has two regions, the reverse bias and the forward bias. So in a similar fashion, we build the device model. However, هيدي بس هيك for your knowledge, in the SPICE simulator, so the previous equation was a hand calculation, يعني نحن قلنا Y equal E to the AX. In the SPICE model, all the transistors or all the diodes or all the models are really simplified to basic elements, مثل some sheet, some resistance, some variable capacitance, and some current source whose current now can be modeled by a set of equations, okay? And at any given point of where the transistor is operating, let us say, as I am simulating, let us say this is 0.5, this is 0. So if this is my input waveform and this is my output waveform, okay, let us say this is my output, this is my input, and let us say I'm operating at this point where the input is 0.5 and the output is really 0.3 at the same time point, and the ground is 0. This current will be function of the specific VGS and VDS at that specific time point T. So as we are solving, we try to, the transistor will be replaced by values of resistance, capacitance, and current. And the current is the usual current equation that we know, but it is a bit more complex. So we're not going to see this structure, don't worry about it, but I'm just trying to tell you how it is used in the context of a simulator. So let us now look at this very basic picture of a 3D image of a transistor. So the 3D image of the transistor has the P-type substrate. We plant the source and the drain region. When we connect them to the signals or to other transistors, right? Because, for example, in an inverter, the NMOS is connected to PMOS at this node. So this node here is going to connect to another transistor, right? So this may go to another device, this may go to ground, and so on and so forth. And the gate will have its own connection. And so between the source and the drain region, we have what we call the channel region. Okay, and this channel region has a distance or a length L between the, if this happens to be the drain and if this happens to be the source, the distance between the two N-type N plus regions is called the channel, and its length is L. Okay, so the channel length is L. So, great. So what is the transistor model and how does it work? There are two things or three things that we're going to learn about the transistor model. First, I need to know what is the threshold voltage, how it is governed, because the threshold voltage is going to determine for me whether the transistor will be off or whether the transistor is going to be on, right? And then if it is on, okay, we need to write the model equations. So we are going to have three model equations, which three types of models. Okay, the first model is the long channel equation, which is the model that we studied in 310. And this really is when the design of the transistor by design, the L, which is the distance between the drain and the source, or the channel length, is really greater than 1 micrometer. Yani for the older type of devices, this long channel model used to hold on well. And then we will have something called the short channel model. We will, or the velocity saturation model. And this one, we will talk about it briefly because this applies when L is less than 1 micrometer. And really, nowadays devices are around 5 nanometer. انتوا بتعرفوا إنه المايكرون هو 10 to the minus 6 and the nano is 10 to the minus 9. Okay, so today's, the future transistor is 5 nanometer. They have realized these chips of 7 nanometer, and today's fabricated chips are in the order of L equal 20 nanometer. Okay, now we will present a unified model. So we will present to you a unified model, and this unified current model stems from the long channel model, but if we call this LCM, the long channel model, okay, plus some effects of the shorted channel, which we call the velocity saturation. Okay, so it will combine the two depending whether the shorted channel kicks in or not. We can then work out the analysis. So it will be similar to the equations that you have seen before with one extra conditional. يعني قبل كنا نطلع إذا VDS is greater than VOV. Now we're going to have the VDS greater than VOV plus an extra condition. Okay, so don't worry about this, but this is what I'm just trying to put the forward plan that is ahead of us. And of course, we will go over one example of another model. If I give you that these are the characteristics, can you analyze? For example, if I told you that y equal ax plus b, and then I changed that, I told you, no, I found a better model, which is ax squared plus bx plus c. Now you should be able to analyze those because these are basic, just mathematical equations. Okay, so great. So this is how we will proceed in the analysis of the MOSFET current equations. Okay, so one more thing that I want to note on this transistor is that if we have a transistor, okay, so let us see if we have a transistor, what comprises the width and what comprises the length, because this is very important. So if I have my transistor, we said that we're going to plant the N plus regions here and the N plus regions here. Okay, and we will see this later as we talk about the layout. The distance, this is the gate tapping from here. The distance here is L between the drain and the source in an NMOS, for example. And this edge here, okay, this edge here, from here to here, is the width of the device. A wider device is going to stretch even further, so it will be wider. So what happens as the device is getting wider? The current flows from the underneath this across the channel from the, if this was D and this was S in the NMOS, it's going to flow from the drain to the source, from the drain to the source. These are all under the gate, under the gate. If the device is wider, I will have more current flowing across my device. Okay, so the current is proportional to the width. You can think of the device as a pipe. It is exactly, this is the drain, this is the switch, this is the source. In this scenario, this is the drain, this is the switch, this is the source node. The current flows from here to here when it closes, and the wider my switch, the more current I will be able to pass through it, so the less its resistance and the more power current it has. Okay, so two dimensions that we care for a lot are L and W. Okay, great. Let us now look at the transistor characteristics. So the MOSFET, we already studied that we have two types, the N channel or the NMOS transistor, where the source and the drain in the N plus regions, and a channel is formed due to applying a gate voltage. So if VGS is greater than VT, I will have a channel. And then the other type of the transistor here, PMOS type, which we said is active low. Okay, and the source and the drain are P plus regions, and the channel forms when VSG is greater than magnitude of VTP. Okay, great. So the transistor is really a three-terminal device, gate, drain, and source, but I also have a fourth terminal, which is the body. Okay, typically for the NMOS, the body node is going to be connected to ground, And for the PMOS, the body node is going to be connected to VDD. It's going to be connected to VDD bil PMOS. Okay, so we don't draw it anymore, but we assume that all the body nodes of the NMOS devices are connected to ground, and all the body nodes of the PMOS devices are connected to VDD. And we explained this, the reason or the motivation behind this was to turn off any parasitic diode junctions that can occur. We don't want those parasitic diodes to happen. Okay, so the bulk or the body, so في عندنا gate source drain. البادي if not shown we don't draw it, so بنصير نرسم الترانزستور like this only with gate drain source, but we will assume that for n channel MOSFETs, for n it is connected to ground, and for p MOS it is connected to VDD. Okay, so this is a given that we will consider for the rest of the course. Okay, حدا عنده سؤال؟ Okay. طب. So, what are the questions that we are trying to answer knowing these characteristics? The questions that we are trying to answer with the current or equations. Later, we want to solve for the DC stable points and noise margin. What is VOH? What is VOL? What are my noise margins? We want to study the delay, so we want to know what is the effective on resistance of my device as it is charging things. So we want to find the time to charge and discharge. We want to perform power analysis, so we want to know what's the current that is being drawn by VDD. And so all of these, I need to know how to model my transistor with. Okay, طبعا we can perform simulation. But the simulators, what they use empirical models. And what we mean by empirical model, يعني بيروح الفاب مثلا at IBM or at Intel, they build all of these transistor arrays, and they start to apply biases of the drain and the gate. And let us say, so what happens here is that you will get VGS stable, VDS stable, and they get the current I. So they sweep those values. For example, VGS equal 0.8 volt, VDS varied from 0 to 1 volt, and then they repeat VGS equal 1, VDS varying from 0 to 1, or 0.1 to 1, and they get those points which we have learned before in VDS versus IDS. Okay, so you will get these curves. هيدي ل VGS equal to 0.8 وهيدا الكيرف ل VGS equal to 1 volt, and then they try to fit them, يعني curve fitting. Exactly as I say, if this is the behavior of Y versus X, you tell me this is the approximate line, and this is your approximate equation Y equal AX plus B. هيدي بنسميها empirical model. يعني أنا I fill in my tables and I try to see what are the best equations that fit my model. So the empirical will assume a mathematical model of the response, which is not necessarily related to the physics. يعني مني مثل أنا بعرف perfectly إنه the current in the capacitor is I equal C dV by dt and I solve the differential equations. No, here we're just obtaining tables of response, VDS, VGS, and I, and we're trying to fit them into the best current equation. يعني find مثلا هون what is the best A and B that minimize the error of the line with respect to these points that I have here. Okay, so هيدا هو empirical model. هلا in real life, okay, Berkeley Beeson group works a lot on these models, وعنده models للبرين نينر FinFET و other devices, and they have these very very complex equations اللي هن pages of equations. So the model كل ما level بيطلع, يعني now we work in level 50 plus, the larger the set of equations it is, and really we now have IDS is equal to function of the bias, but in this function I will have a lot of parameters and equations. Okay, and these lot of parameter and equations, the parameters are built into what we call the model card. Yani for example, this is the level, this is the, if I find VTH0, this is VTH0 of the transistor, this is the oxide thickness, we'll talk about them later, and many other more. This is VSAT, for example, we will tell you what the saturation velocity or what the saturation effects are. Okay, so yes.
بس يكون في 3 pins للموسفيت وين بتكون موصول البيز؟
Okay, so when we have 3 pins for the MOSFET, we said for the NMOS, we will always assume that the body is grounded, and for the PMOS, we will assume that the body is connected to VDG.
Yes, but as an electronic component مرات بيجوا 3 pins.
بيكونوا عاملين له shorting إذا أنت عندك a discrete one that is already fabricated, and if your discrete has only 3 pins, then what they do with it is they short the body to the source node. Okay? So this way VBS or VSB will be equal to 0. But for our purposes, unless we tell you by default it is connected this way. Okay?
Professor?
Yes.
Why would I use an empirical model if I have the exact equations?
Because there are no exact equations for these complex nonlinear devices. يعني the capacitor, we know how to, that it is I equals CdV by dt, right? But the transistors, they are so small now that their current cannot be modeled by a known set of equations. Yeah, okay, we try to have semi-empirical, semi-physical behavior, but the number of equations, يعني look here, مثلا beta 1 times this is beta, what it is equal. You have all of these parasitics, so really the transistor model is a very complex network. يعني كيف الdiode we built it, let me, sorry. Did you see the diode model that we drew a little bit ago, this one here? Okay, you can consider now that they built the transistor model as a complex network of RC and current sources, dependent current sources and stuff like that, and work function and etc. And all of this complex network is governed by a large set of equations, اللي هو المودel which is built by Berkeley. But the parameters of this model, that we have here are determined empirically from the measured device dataset. Okay. يعني بيتفقوا ببركلي, they say that, well, this is the complex model that I'm going to do for the transistor, and this should be a decent complex set of equations, but go ahead and fit for me the parameters using the data that you collected from the fab. Actually, there is an initiative now that is led by UIUC. One of them is who used to be my advisor, Lise Rosenbaum, and along with other, and she's the student of the main professor at Berkeley. They are trying to use now machine learning to see if it can replace really those different levels of models that have been historically maintained by Berkeley, to when we collect the data from the chip to build the models for those transistors. يعني fully empirical, يعني this is semi-empirical maybe. There are some characteristics that we know for sure should be included. For example, the work function, the level, the forward bias, etc. For example, VGS minus VFB. We know this. Okay, all of this that come from intuition, they're trying to say, well, what if I want to build a black box model? How good is it going to be? Now, typically, so far, those semi-empirical models have succeeded in capturing the behavior so far very well. And this is how is this validated? It is validated by the fact that when we get this data from hardware, plug it into the equations, and then the designers are building all of these chips starting from the assumption that the simulator should behave this way. sending it to fabrication and they are meeting their requirement, this means that the hardware agrees with the model because we are successful so far to design based on these equations and to get the chip to work in real hardware. Okay, so it is an approach.
In this case, every fabricator would have his or her own set of equations for his device.
Right. If your design is built in your own fab or for a specific technology حتى, لأنه remember that they will design different technologies targeting different types. يعني عندك الانالog, if you look at cadence, for example, you have the digital, you have the low power, you have the high performance, right, and the low power. So you have the memory. You will have design for the memory, for the SRAM, you have different design for the DRAM. So every type of fabrication, the devices are optimized for it. There is going to be a separate model for these devices. They all stem from the same mother or parent technology, but they will have a special treatment in the design process to make it optimal for memory or for memory density, to make it optimal for low power, to make it optimal for high performance. يعني هيدي tolerate faster, يعني tolerate higher VDD, etc. etc. So it's exactly like buildings and bridges and stuff like that. Okay.
Thank you very much.
Okay. Thank you. Yes.
When you say level, what does it mean? إنه هون level 5 وعم تقول level 50 plus or no?
Hey,
What does
بزيد
it mean level?
complexity. With the level, the complexity increases of the model.
Okay.
يعني the equations will increase and the model will become more complicated. Okay? Okay, great. طيب هلا you will not deal with this, but this is just general knowledge. So the first simple step that we need to look at is really the MOSFET threshold voltage. لأنه the MOSFET threshold voltage will determine if it is on or off, and will determine if there is a current or no current. So the famous quotation, to be or not to be. Okay? So to look at the MOSFET threshold voltage, هنرجع نعمل refresher again. إنه if I have a basic NMOS transistor, the body is grounded. I start, how do I find what's the threshold voltage? The source and the drain are grounded, and I start to apply voltage VGS at the gate node. Okay, so what happens first is that in my MOSFET, initially this is purely P-type. Okay, and then what happens as I start to increase the gate voltage G, it starts to push away all the charge from this region. So we call this the depletion region. شو يعني depletion؟ يعني depleted from charge. يعني هو أنا كان عندي holes, I used to have holes in the P-type and it pushed them all away. فرغتها, it vacuumed it from charge. And then, so the depletion region forms and the mobile holes are initially pushed away. Here سميناهم. After this, as I start to increase VGS, okay, so as VGS increases, it will start to, we will start to have mobile electrons after that to appear at the surface. يعني هون they will start to occupy the surface. And when VGS is large enough, for large enough VGS, okay, such that the density, يعني density of electrons at the surface becomes equal to the density of the holes below. يعني هون if the holes have a certain density, طبعا هيدي you will not use this fact when we solve this, I'm just telling you what it is. When the density of the holes here becomes, when the density of the electrons becomes here equal to the density of the holes, we call this a strong inversion. بيصير في عندي شيء اسمه strong inversion. يعني أنا بكون قلبت ال P-type ل fully N-type material, بيصير عندي ال N-channel. So the strong inversion, the N-channel forms. Okay, بصير في عندي channel, and this means when I reach the strong inversion, this means I have reached my VT. So بس تخلق channel, I will reach VT, and when VGS becomes greater than VT, I maintain this channel, I will have an overdrive, and I will have the current later flowing لما بحط drain voltage different from zero. Okay, yes.
Doctor, can you repeat امتى بيصير في strong inversion؟ بخص
لما
electrons.
VGS بتوصل على الليفل للVT بكون أنا عملت الانفرجن، بكون فتت بالسترونج انفرجن region. اوكي، يعني when I exceed the density of the يعني بس وصل على الليمت انه number of electron density بيساوي الهول density بكون عملت فتت بالانفرجن. و as I increase VGS greater than VT, I start to have more electrons, to have higher current. ما هو in the end, let me erase all of this. So in the end, let us look at it here. What is the current? Later we will draw this and understand this, but let us draw it from now. What is the current in the saturation region? شو الكارنت؟ ما هي I equal half K prime W by N ضرب VGS minus VT all squared, right? So as VGS becomes much larger than VT, when VGS is much larger than VT, I will have a good density, okay, of the electron density in channel will increase, صح? And this means that, pardon me, and this means that the current I will increase, صح? But I need the channel to form in the inversion layer to be able to conduct, okay? So when I start to attract the electrons, I will measure roughly, يعني هي أمتى ال VT منقيسها as function of VGS لما الكرنت يصير أعلى من zero, right? لما الكرنت يطلع عن الزيرو بنقلب على الأون ستيت. When I reach a strong inversion بيكون عندي large VGS أكبر من VT, and this I call the strong inversion. Okay? فإذا the steps are: number one, the small VGS greater than zero is going to push away the holes, حتفرغ لي region. Then VGS will increase to the extent that some electrons will start to appear. This is called weak inversion. And even larger, if VGS keeps increasing, I will have stronger inversion, and I will have current that is increasing with VGS greater than VT that is flowing in my channel. Okay? So أهم شيء نعرف إنه I is proportional to the electron density, and that this is proportional to how much VGS grows above VT, right? That's what matters really. Is this clear?
Professor?
Yes.
وقت يكون عندنا weak inversion في current.
It's very weak. يعني if the electrons exist بس تطلع الI أكبر من زيرو معناته أنا فليت من الcut off، صح؟ يعني if I have a thin channel,
Yes.
I have a very small current. هلا the VT empirically really depends what we determine as the cutoff current that we consider as on, right? صح؟ But when VGS exceeds VT, it keeps increasing. The density للchannel بتصير electron density بتكبر مع الكرنت اللي عم يقطع عنا، صح؟ Up to a certain limit طبعا. Okay? So the definition of VT exactly between weak and strong, don't worry about it. But what matters to me is that, you know, first there is only holes, then there is a depletion region as VGS increases. Then as VGS exceeds VT, بنبلش نقوي density وبنبلش نقوي the current will become stronger. Okay? Great. So this, in terms of the threshold voltage, هيدا عم يشرح لي كيف بيصير depletion region, and then he's explaining to me that I will get the channel, and when the N channel exists, so the value of VGS, and it is relative, where strong inversion occurs, is called the threshold voltage. We can assume that this is the limit when the density of electron بتساوي بالchannel بتساوي density of holes in the P substrate. صح؟ يعني in the body, right? In the body. We can assume that this is the value, يعني it's a definition, right? Don't worry about it. Okay? بس بدي يكون عملت channel وصارت dense enough for me to consider that I have a decent current. Okay? طب, great. So let us now therefore look at the gate, source and drain. Therefore, when it is off, this is an open circuit between source with drain. And when it is on, so this happens when VGS is less than VT. And for our purposes of the analysis, it acts as an R-on when VGS is greater than VT, right? يعني بنعتبر إنه في sufficient current for it to be considered as an on device. Similarly, for the PMOS device, in a similar fashion, we assume that for the gate voltage, when VGS is less than VT in absolute value, أو لما VSG أقل من absolute value of VTP, that it is off, and we assume that it is on when VGS in absolute value greater than VT, or VSG is greater than magnitude of VTP, that we can model it as an on resistance. Okay, great. طب هلا هون, sorry, this is, I thought that this was copied to the okay, so here, but the threshold voltage is really function of VSB. يعني the voltage from the body to the source, or the source to the body matters. ليش؟ لأنه نحن when we put this is the gate, drain and source, okay, and I have the body is always grounded, okay. If the source is not grounded, I will have some effect on increasing VT of the device. Okay, if the source is not grounded, I have some effect on increasing VT of the device. And this has to do with the fact that هيدي N plus وهيدي P, if I have the diode, هيدي البادي, right, هيدي البادي grounded وهيدي source grounded, then V diode هون zero, صح؟ طيب, بس if I have the source voltage in another diode, مثلا على 0.1 volts, يعني أنا هيدا الترانزستور بطل هيك, صارت هيدي 0.1 مثلا, وهيدا الجيت is 1, وهيدا الدرين عم تتغير, okay, and this is still grounded, مش هاي P هاي N. What happens here is that V diode becomes equal minus 0.1. So what happens is that this is going to increase the barrier in the device. يعني هيدي, if you recall, the depletion region becomes wider as the reverse voltage increases. And this depletion region interferes non-linearly with the transistor effort, with the gate ability to push things, okay, لأنه صار في حدا another positive voltage, and therefore this delays the onset of the channel. ما حنفوت بالفيزيكس كيف. And therefore, mathematically, what matters to us is that we can conclude that there is an equation that says, well, you have to inspect what is your VT as function of VSB. So for the purpose of the current equation, what does this mean? This means that we initially find VT, and if I give you a transistor which is operating at some drain voltage equal 1, some source voltage equal 0.1, and some gate voltage equal 1. First you tell me, oh wait, VSB is different from 0, so VSB is equal to 0.1. We calculate VT, and then we use the current equation as we know. Okay, so all of this saying is that VST of VSB هي VT0 يلي هي لما VSB equal to 0, and we give it to you, this is a given, plus some constant gamma times an equation, وهيدي الإيكويشن هي absolute value, فيكم تطلعوا عليها square root of absolute value of A plus VSB, okay, minus the square root of absolute value of A. Okay, so we can look at it this way. Where did this equation come from? It comes from the work function and the potential barriers inside the device. And the idea is that we know the definitions. VT0 هي threshold voltage لما VSB is equal to 0. It's a property of the material. VSB is the operating source bulk voltage. Gamma is another empirical parameter that is fitted. It is the body effect coefficient. And phi F is some potential يلي هو function of the material of the device. Okay, فإذا I have an equation, I have a set of empirical parameters. If I know what my VSB is, I can fit and find the parameters for my VT before I start using it in my current equations. Okay, so it is very simple. So why would the body effect kick in? We looked at the NAND gate. In the NAND gate, we saw that I can have two stacked transistors, صح؟ هيدا ال A وهيدا ال B. طيب, if the body is grounded and if this node is grounded, the lower transistor B has the source and the body at ground, so ما عنده body effect, right? But the upper transistor, if I assume that during a transient behavior, that this is R on A and this is R on B, okay, as I'm trying to charge or discharge, this node is guaranteed at 0. Is this node guaranteed to be at 0 all the time during operation? At steady state, yes. But as I am operating, no, it's a node between two resistors. It might be charged. So there is nothing that guaranteed that this SA is equal to 0. And it might be positive. And therefore, this transistor has a body effect and its VSB is different from 0. Okay? So if the source node is positive, at some operating point, and it will be given and very well known. Example, when two transistors are in series, then VSB is positive. Okay. Hella, in this case, let us look at the trend here. So somebody collected as function of VSB, the substrate bias voltage. Okay, the threshold voltage VT, as VSB is increasing, the threshold voltage is also increasing. So let us look at the equation here. If we assume that VT is 0.4 volts and this is positive, let us say this is also 0.2, for example, times. If VSB is positive, this is minus 2 phi F كلها سوا بتطلع positive. يعني let us say this is 0.6 plus VSB, okay, minus the square root of 0.6, right? So anytime my VSB is positive, this term is going to be greater than 0, and I'm going to have a term added to my VT0. Okay, so in this scenario or in this example, we will have VT when VSB equal, for example, to 0.2. It is going to be equal to 0.4 plus 0.2 times the square root of 0.6 plus 0.2. It is 0.8 minus the square root of 0.6. So we will end up having VT greater than VT0. Okay, and it's simple math. Okay, so this is simple math, and the equation here and the drawing here shows us that this behavior also holds captured in real measurements. Okay. In a similar fashion, we have an equation for the PMOS. In the PMOS, this node is connected to VDD body. So if VSB is 0, I will have VT equals to VT0. However, when VSB is negative, يعني when VS is less than VDD, which is possible if I have two series transistors here, هيدول موصولين على VDD وهيدا الأوت. This source node is VDD, but this source node for this transistor is not guaranteed to be at VDD. So we can have VS less than VDD and hence VSB is less than 0. In this case, I will have the PN junction will be reverse biased and I will see an effect of increasing VT. Okay. So for okay, so somebody is asking me about whether I will be posting practice problems for the short quiz 1 on Friday. For the short quiz 1 on Friday, please practice the homework, because definitely there is going to be a question about the yield. There's not much to practice there in that session. You have the equation for the delay. Okay, the RC delay time constant. You have an example, so try to practice along that line. And you have the equations for the, if I am correct, for the the chain of inverters, and the equation is very clear and obvious. Yani. So some of the questions are very straightforward, and you don't have to worry much about it. But please practice the homework problem number 1. That's why I posted it to be due before the exam. I will post the solution for problem number 1 on Moodle at 5 p.m. on Thursday. Okay? Anybody has any questions? Thank you, Karim. طيب, thank you everybody. And
دكتور
yes, go ahead.
بس لأتأكد هيدا كله اللي عم نعمله هيدا اليونيفايد موديل منا باللونج
لا لا لا، بعدنا هلا عم نحكي عن الفي تي. إذا
أوكي.
تنتبه عماد، نحن حطينا بالسلايد قبل إنه أول شيء بهيدي التشارت بدي أتعلم الفي تي شو حيصير فيها on or off. And then we will talk about the models. So now we are saying, well, given a device with a certain bias, what will be its VT voltage? أعرفها إذا off and on, and later I will use this VT in the current equation.
اوكي
Okay, and هي applies the long with short. Okay. طيب, yeah. Anybody has any other questions? Thank you.
إيه أنا بس سؤال بس.
Yes.
متى هو رح تكون ال problem solving session؟
The problem solving session بعد after we finish the IV characteristics. يعني بدي أقطع لكم بالثري مود بهيدي وبالتو models, regular will unified. I will start to put the problem solving session. I will give it to you about, it will be a lecture about يعني during class. Okay.
Okay ماشي.
Class time يعني, don't worry. And I will also post it online so that you have chance to ask questions as well.
Okay, thank you.
طيب, thank you very much everybody. يلا, take care.
Thank you, doctor.
Thank you.
Goodbye.
Bye.